Due to a variety of unforeseeable circumstances in a recent case of mine, which I am unable to disclose to the public, I have been given the choice of either a 6-month incarceration or an undetermined amount of community service. So I of course chose the latter, and I will be doing so in the form of chemically based educational videos. Now, we will begin today with reading the periodic table and discussing orbital sublevels, just the definition, periodic trends, valence electrons, and some of the most common types of bonds. Now, the good thing about the periodic table is that it generally lists most of the information that you will need to know as a novice. So, in the top left-hand corner is the atomic number, which is the number of protons and electrons, unless it's an ion. And the atomic weight is under the name of the element. The symbol is the giant letter. And conveniently, this table actually lists the valence shell configuration as well, which we will get into later. Everything on the right of this zigzag line, right here, are nonmetals, and everything on the left is metals. The purple indicates transition metals. This is conveniently color-coded. Alkali metals, alkaline metals, noble gases, which appear as pairs in nature and are extremely non-reactive. Everything touching this zigzag line, with the exception of aluminum and polonium, are metalloids. Now, some of you may be wondering why the lanthanide series and the actinide series have been separated from the rest of the transition elements, and this is mostly for aesthetic value, but the lanthanide series all are derived from lanthanum, and the actinide series act very similarly to the lanthanide series and are generally derived from actinium. Something to keep in mind is that the A groups, so this, all of these, a number related to the A groups corresponds to the amount of valence electrons within those groups. So, for example, lithium will have 1 valence electron because it is in group 1A. And so on and so forth. The B groups and the transition metals are separate. You don't need to worry about them unless you are going on to more advanced chemistry. And the valence electrons are different. They have to be memorized and generally have a charge of either +2 or +3. Now, while we're here, I will define orbital sublevels, which will come into play later on when we discuss valence electrons and electron configuration. So, there are 4 orbital sublevels, 3 of which we will discuss. And the orbital sublevels, as you can see, are S, P, D, and F. F are not needed as of now. They are generally very, very reactive and synthetic, and we don't need to worry about them in basic chemistry. But before we move on to periodic trends, we are going to need to look at a few definitions. Now, 2 useful definitions are electronegativity, which is a chemical property that describes the tendency of an atom to draw electrons towards itself. And of course, ionization energy, which is the energy needed to remove an electron from its orbit around the nucleus. Now, this next part should be a review, but for clarity's sake, I will describe the basic shape and parts of an atom. So, all atoms, for those of you that don't know this, are composed of a nucleus with a surrounding cloud, which is a very oversimplified and somewhat incorrect term, but for this, it's fine, of electrons, which are much, much smaller than the nucleus, and the nucleus is made of protons and neutrons. Number of protons never ever changes. That is what makes the element the element. The amount of neutrons can change, considered an isotope, but we are not getting into this today. So, the nucleus is made of protons, and neutrons, which for the most part, nucleus stays the same. And of course, there are a variety of different levels, again, oversimplification, of electrons in shells outside, floating in their corresponding sublevel. This is needed to properly understand what a valence electron is and for understanding ionization energy, which is related to valence electrons. Now, the outermost layer, the outermost shell, is called the valence shell. And it is related to valence shell configuration, which we will get into later on after periodic trends. And this is the shell farthest away from the nucleus, so it is the bond between the protons here in green and the electrons here in blue is weakest on the outer shell because it's farthest away, so it doesn't have as much of a pull towards it. It's very hard to remove. It's nearly impossible to remove the innermost layer of electrons, but how you make bonds and compounds and such are generally related to either giving or receiving valence electrons. So, with that in mind, we will move on to trends. Elements tend to get less metallic and smaller across a period, but they are more metallic and larger in size down a group. The more metallic atoms are, is just the more they act like metals versus nonmetals. Ionization energy, however, increases across a period, but decreases down a group. And that is because the larger you get, so the more electrons you have, the easier it is to pull an electron away because it is farther from the nucleus and thus farther from the proton's pull. Electronegativity follows this pattern of increasing along the period and decreasing down a group. For example, iron is smaller and less metallic than gold. With a basic understanding of valence electrons and the periodic table, we are able to move on to electron configuration and orbital diagrams, which is a way of displaying where the electrons are within the orbital sublevels that we discussed earlier. For example, carbon has 6 protons and electrons, unless it's an ion. In which case it will have a different level of electrons, but as we stated earlier, the protons always stays the same. You begin by writing the orbital sublevels and add in the amount of electrons that are in those sublevels. So carbon is 1s2 because each s level can only hold 2 electrons, each p level can only hold 6, each d level can hold 10, and each F level can hold 14, but as we discussed, we are not getting into F. So, carbon has a total of 6, and in order to have 6, you have to fill the first S level. The second S level are completely filled, and P comes in on the second period, so there is no 1P. It just starts at 2. The remaining level, which is 2. So, of course, if you add the number of electrons, it equals 6, so you know you did it right. And another way of visually representing the same thing is something called an orbital diagram. So, using, again, carbon, you can draw lines for each space. Each individual orbit within the sublevel can only hold 2 electrons. Much like people electrons are very finicky and they prefer to sit by themselves before sitting with strangers. So you must fill the first spot of each orbit before moving on, and you must fill each prerequisite orbit before moving on to the latter orbits. So, 1, 2. And the arrows are opposite because each electron within each orbit has to, they rotate in opposite directions. So you just go like that. And again, do not add this before this. So that is an orbital diagram. And with all of that in mind, we will discuss a little bit more about valence electrons, because they are generally what is most involved when discussing bonds. So valence electrons are important because if you take or give valence electrons, you will create what is known as an ion. This is just an atom with a charge of some kind. Giving an electron results in a negative charge, because since electrons are negatively charged, if you add more electrons than there are protons in the nucleus, then the atom as a whole is negative, has a negative charge. And if you take away an electron from an atom, it will have a positive charge, because you are taking an electron away, so there's one more, well, however many, there are more protons in the nucleus than there are electrons in the surrounding shells, rendering the atom of a positive charge. Now that we understand atoms, we can discuss some basic bonds, which are covalent bonds, ionic bonds, and hydrogen bonds. Now, covalent bonds are bonds where two atoms share electrons. So an electron essentially just goes in and out of, say, carbon and oxygen. Now, there would most likely be more atoms involved in this bond, but for now, we're keeping it simplistic. A good example of a covalent bond is NaCl, which is more commonly known as table salt. And there are also ionic bonds, example of which is lithium and fluorine. Lithium has 1 valence electron, and fluorine has 7. So this is fluorine, and it is attracted to lithium because atoms always want to be stable. So, and a stable shell has 8 electrons in it. So since fluorine has 7 already, it is much more likely to take an electron from somewhere else than exert the energy to give away all 7 of its valence electrons. That would be really inefficient. Lithium only has 1 valence electron, so it is much, much more likely to give away its electron than it is to take 7 from somewhere else. And this leaves lithium stable. It is stable with an outer ring of 2 electrons. The innermost ring of electrons is stable with 2, and every ring outside of that until you get to a certain level is stable with 8. The visual representation I have here, listing only the valence electrons and seeing how they come together to form bonds, is something called an electron dot formula. So it is the name of the atom, or the symbol of the atom, with its valence electrons placed around the symbol, and there can only be 2 in each spot. So this is not but carbon only has 4 valence electrons, so it would only have 4 listed, unless it were to bond with something else. And our final bond for the night is hydrogen bonds, which are extremely important for a lot of things. It is what keeps the double helix of our DNA together, along with a variety of other things. So hydrogen bond is what keeps a water molecule held together, and it is a relatively loose bond. The strongest bond that we talked about was covalent. The next strongest is ionic. And as I said, hydrogen bonds are relatively weak. It is a hydrogen atom, generally in a compound, but not necessarily, which bonds to either oxygen, nitrogen, or fluorine, and it's generally a slight negative charge, but you don't need to get into that. And this concludes the first video in what will be a series. Later on there will be some hands-on experimentation, some of which you can do at home, so stay tuned for that. And if you have any comments, questions, or concerns, please feel free to direct them elsewhere, as I am not wasting my time.